Welcome everyone to the 7th Juice webinar. Today we will talk about the collaboration and synergies between two missions that are currently on their way to the Jupiter system, Juice of course, and Europa Clipper. We have 4 speakers lined up for you. The first to talk will be Claire Vallat. She will present a short update on the status of Juice. Claire is with the Juice team. She is the operations scientist and deputy project scientist, and she works at the European Space Astronomy Center of ESA in Spain. After that, we will hear the status of the Europa Clipper mission from Robert Pappalardo. Robert is a fellow and senior research scientist at NASA's Jet Propulsion Laboratory at Caltech. And he's the project scientist for the Europa Clipper mission. Kaya Hayakorth will help him change the slides as Bob is not in position to do that very easily today. Then Emma Bunce from the University of Leicester will be speaking. Emma is a co-I on Juice instruments, JMAC and UVS, and she's also a co-chair of the Juice Clipper Steering Committee, and she will speak in that capacity. And at the end, the final talk will be by Mathieu Choukroun, who is working at JPL. And Mathieu will talk about the Clipper part of the steering committee. Mathieu is an investigation scientist for mass specs on Europa Clipper and a facilitator for the Juice Clipper Steering Committee. Since we have a lot to go through, so we will not delay any further. Without further ado, Claire, the floor is yours.
So hi everyone. So for those who didn't attend the last webinar, I will give a short status update, which is what happened in the past, let's say, couple of months. So yes, the first thing that we want to say today is that it's been more than 2 years now that we are in space. So we celebrated that in April, and we are 1/4 of the total cruise phase on our way to Jupiter. So we've already done quite a lot towards our final target. So this is how the cruise looks like, and this is where we are at the moment. So what you can see on the right is the current path of Juice in the inner solar system. So we have completed our second revolution around the sun. On the left, you can see like a summary plot where you see the distance to the sun in orange and to the Earth in blue. Of Juice, and we are, as you can see here, at 1/4 of the total cruise. Our cruise is basically following an Earth, Venus, Earth gravity assist pattern, and we have performed last summer the lunar Earth gravity assist, and I invite you to actually look back at the webinar that we gave earlier on, the Europlanet webinar, where we explained all let's say, the challenges and the science and the results that we got from this exceptional event. And our next, let's say, stop, even if it's not going to be a stop, will be the Venus gravity assist this summer. I will say a word about this a bit later. And the small triangle that you can see here are actually in blue and in green, the moment where we are planning to operate the instrument for checking the calibration and performing a reference measurement. And you can see at the bottom, yes, the yellow triangles that corresponds to the gravity assist during the cruise phase. So for those who are not familiar with Juice, so Juice is on its way to Jupiter to study the Jupiter system. It's a very broad and interdisciplinary mission. The main objective of the mission is to study the icy Galilean moons and their habitability, and to characterize in particular their interior and their subsurface ocean. But let's say the prime target of Juice will be Ganymede, which has a key set of characteristics that we want to study further, and the focus of the end of mission in particular will be on this moon. I will say a word about this later. But of course, we need to study those moons in their complex environment. So the Jovian system is a very complex environment with many different parts: the rings, the inner moons, the irregular moons, and the huge magnetosphere, and of course the gas giant that is, let's say, responsible for many interactions, complex interactions, which also affect and impact the characteristic of the icy moons. So we have a very complex and complete set of payload. We have several remote sensing instruments which cover a very large wavelength range from the UV to the infrared, visible, and sub-millimeter wave. We have also a laser altimeter to study the topography and the tides on the moons. We have ice penetrating radar to characterize the icy surface of the Galilean icy moons. And we have also a complex set of in situ instruments to study the plasma, the waves, the electric and magnetic fields that are embedded, within which Juice is embedded. And last but not least, we have also radio science instrument that will support the investigation, of course, of the interior of the moons. So the mission design is actually kind of two missions in one. So there's a first part which will be a Turing-like mission where we will be in orbit around Jupiter during more than 3.5 years, arriving in 2031. And during this phase, we will perform many flybys of the icy moon. So the current trajectory foresee 23 Callisto flybys, 2 Europa flybys, and 11 Ganymede flybys. And we will also use those flybys, and especially the Callisto flybys, to incline the orbits and to go at higher latitude in order to visit a new region of the magnetosphere of Jupiter, and also, of course, have a very interesting viewpoint of the poles of the planet. Then we will come back to the equator, and late in 2034 we will enter in orbit around Ganymede. We will start with a period of observation at a circular orbit at 5,000 kilometers to provide a global, let's say, mapping of the moon. And then we will go in orbit at a lower altitude at 500 kilometers. And this is, let's say, the latest news that we have now is that due to the very excellent performance at launch, we were able to save sufficient delta V to actually add as the last part of the Ganymede phase, which is at the end of the nominal phase, 1 additional month where we will go as low as 200 kilometers altitude around Ganymede, and which will, of course, provide invaluable conditions to study further the interior of the moon and also the complex plasma environment close to the moon and the ionosphere in particular. So, yes. So before we reach Ganymede, of course, we have to get there. And as I mentioned at the beginning, we are now on our way to Venus. We will fly over Venus on the 31st of August this summer. Unfortunately, we have a very stringent constraint in terms of communication and thermal constraint as well. So the payload operation will be limited to the radiation monitor. But this is a key, let's say, a key activity for us to put us en route to the Jovian system. And I just want to say a word to really introduce the very interesting talk from Emma and from Mathieu, the speaker that will follow, because as you know, we had the chance to see a wonderful launch of Clipper last year. And we are now ensured to have the 2 spacecraft in the Jovian system at the same time for significant duration. And this, of course, brings invaluable opportunity for synergistic science. And this is actually the work that Emma and Mathieu has been doing. So with this, I think I will stop.
Now a brief update on the status of the Europa Clipper mission. Greetings from downtown Los Angeles, where I've been called for jury duty that follows this meeting, doing my small part to uphold the rule of law in the US. Next slide, please. Europa Clipper launched in October of last year after delay from Hurricane Milton. And hopefully that was all the bad luck because things are going just great with the spacecraft. Next, please. The October 14th launch date put our Mars Gravity Assist on March 1st, so very recently. And we are currently moving toward apoapse, where we will then come into a flyby of Earth in December of next year. And then with a gravity assist from Earth, head out toward Jupiter orbit insertion in April of 2030. Keep in mind that Europa Clipper science currently focuses on Europa only. So our tour has 49 science flybys of Europa, generally at altitudes 25 to 100 kilometers, with several opportunistic flybys of Ganymede and Callisto to shape the orbit. Next, please. The spacecraft is healthy, operations are stable. Spacecraft recently reached 2 AU from the sun, so the high gain antenna can now remain pointed toward Earth. There was a thermal constraint before that, so we're now getting continuous high data rates. The nominal altitude here in cruise maintains the spacecraft power positive and thermally and dynamically stable. The attitude is controlled by reaction wheels currently with periodic thruster biasing. The radiation monitor engineering system remains powered on. And key activities include that flight system checkout has been completed. A couple of instrument activities were postponed due to the terrible fires in the Los Angeles area back in January. All instruments have now been turned on and undergone initial functional checkouts. All maneuvers have been executed with excellent targeting and nav performance, and the Mars Gravity Assist was right on target at a flyby altitude of 884 kilometers. We'll talk more about that in a moment. We had a successful post-launch assessment review back in March. Next slide, please. So the Gravity Assist on March 1st provided a wonderful opportunity to calibrate and test 3 of the Europa Clipper investigations. The thermal emission imaging system acquired data at Mars to test an algorithm to correct a nonlinearity in one of the bands. So for calibration, taken a day out, and a region that was also measured by instruments in orbit at Mars. The radar, Reason, performed its first end-to-end comprehensive test. That couldn't be done on the ground beforehand. The data has been coming in and looks fantastic. And MRO's Charade obtained data the same area just a bit earlier. The gravity and radio science procedures and processes were tested successfully as well. And that stored data, now that returned to Earth, has been coming back. So next, please. We had a public release just recently showing the Themis image at Mars, showing surface temperatures as bright or warm here. And analysis is underway to understand how the algorithms for correction of the nonlinearity in that one band are doing. You can see on the right, especially the diurnal thermal signature with geologic and topography overlay. Next, please. Quick status on the instruments. The ultraviolet spectrograph obtained first light, had its high voltage checkout recently. The Europa imaging system, the narrow angle and wide angle cameras successfully obtained dark images, and the checkout of the narrow angle camera gimbal is complete and successful. The covers for those cameras remain in place until July of 27, so we reach 3 AU. The mapping imaging spectrometer The scanner initial health checks are successful and complete, and it won't be able to operate in science data collection mode until beyond 4 AU, once it's colder. Let's see. The imaging thermal emission imaging system, as I just mentioned, had a successful calibration at Mars, and the Reason radar end-to-end test was successful with the data processing ongoing. Reason will soon have a beam pattern characterization using the Owens Valley Radio Observatory. That'll happen in the coming month, and looking toward early winter, late fall, the Milky Way scan will be forthcoming as another check on the system. Next, please. The Europa Clipper magnetometer boom was successfully deployed back in November, and ECM has acquired data for checking on any electromagnetic interference during the instrument checkouts. So that data is currently being analyzed. Things are looking good to date. The plasma instrument completed the checkout, and during that checkout, it seems that there was low density and fast solar wind, and that's indicating that the instrument turned on in the turbulent wake of a coronal mass ejection, which is exciting. The mass spectrometer for planetary exploration, our neutral gas mass spectrometer, has checked out with limited high voltage, and its vacuum door doesn't deploy until after the Earth flyby and we reach beyond 2.2 AUs in early 2027. The instrument won't be full up with its calibration gas system until the first Ganymede encounter. The surface dust analyzer checked out with limited high voltage. That's completed. Its cover doesn't deploy until 2.3 AU, early 27 after Earth flyby. And finally, I mentioned the gravity and radio science had a successful checkout during the Mars flyby, and the telecom system has checked out the X and Ka band calibration. And next, please. Additional events coming up are characterizing the high gain antennas Ka band foresight. Oh, I'm sorry, that's been completed. It will lead to use of the Ka band downlink soon. Flight software update is planned for August, with which will increase robustness against several small anomalies found during V&V. And it will enable functionality of the MOSFET Canary box, which will allow for measurement of voltages of several of the MOSFET parts in this box, which duplicate systems on Europa Clipper, so we can make sure our MOSFET transistors are behaving as expected. There'll be a self-compatibility activity. The first round of checks will focus on spacecraft component interference, and that'll be followed in outer cruise once all the covers are off with a full checkout of all the instruments and their compatibility. Very exciting time for the team as these checkouts occur and we start preparing for the Earth flyby next winter, a year from winter, December of 26. And my last slide, if you have your phones handy, go to that link there, and you can see all 18 papers now published online from the Space Science Review's topical collection on Europa Clipper, which highlights the science objectives, the mission, the spacecraft, the instrument investigations, all there for you to download with open access. The deputy project scientists, Haya Korth and Bonnie Barati, have successfully herded all of the cats to get these papers together. An amazing job by the science team in putting this collection together. And that's it for the Europa Clipper update. I appreciate it.
Good afternoon, good evening, good morning, wherever you are. It's great to join you all for this webinar this afternoon. My name is Emma Bunce, as you've already heard, and I'm going to be talking just for the next 15 minutes or so in my capacity as co-chair of the Juice Clipper Steering Committee. And that's an informal group of people shared between the Juice and the Europa Clipper science teams listed here, who've been working together over the last 2.5 years to explore the potential opportunities for joint science from our two fantastic missions. The output from this work so far is 2 reports. We've looked at science opportunities during cruise and approach, which Mathieu is going to talk about after me, and also more recently a report on the science opportunities during the main orbital phase, and that's what I'm going to focus on now. So I'm going to start with a summary. So basically, the presence of 2 flagship class well-instrumented spacecraft in the Jovian system really provides an unprecedented opportunity to increase the science return possible from each mission alone. And it's a situation that is very unlikely to happen again anytime soon. So we're really very excited about the possibility for this collaboration. During the orbital phase, which is when both spacecraft are operating in the Jupiter system, our committee have looked at about 100 science objectives, which are possible across multiple different target areas, including Europa, Ganymede, Callisto, Io, the rings and small satellites, Jupiter's atmosphere, and Jupiter's magnetosphere. And all of these objectives either require or significantly benefit from 2 spacecraft observations. For each of these objectives, we've looked at the top level measurement requirements, and we've also looked at which payload instruments would be required to deliver those potential objectives. And I just wanted to note here that all of these objectives require a sort of different level of collaboration between the 2 missions. So as you can see in the blue boxes there, I've highlighted the types of measurements that are required, which are synergistic in nature. And by that, we mean that it's only possible to achieve the science objective because we have 2 spacecraft. And those objectives split into both simultaneous in terms of temporal observations or synchronous observations, or they're observations that can be done separately, but they need to be coordinated. And then we also have complementary measurements, which are those measurements which can extend an existing science goal because we have additional coverage, and also include measurements like cross-calibration, which I'll touch on later in the talk. So the other thing I just wanted to mention very briefly, but Mathieu is going to talk more about this, is the fact that after Europa Clipper enters orbit around Jupiter, there's an opportunity for high priority science during this approach phase. And the group have also made a point of advocating for coordination with ground and space-based assets during some of these measurements. So we've looked at an initial assessment of the science priority and how easy or otherwise it would be to implement these objectives. And this is ongoing work. But as you've already heard from our introductory speakers for Juice and for Clipper, obviously the most exciting and important news in regard to joint collaborative work is the fact that both spacecraft are now on their way to the Jupiter system. So it's the 2-year anniversary of the Juice launch has just gone by, and just over 6 months since Europa Clipper launched. And importantly for this joint collaboration, it confirms the timeline that we have, and it confirms the fact that we have a significant opportunity to operate the 2 spacecraft together. So our studies, just to mention, have used the pre-launch trajectory, so we haven't updated it for the updates that Claire's just given us about Juice, for example, and we would be implementing the up-to-date trajectory in future iterations of our work. But really, the first step for this group is that we needed to get to know the joint trajectory. Seems like an obvious thing to say, but actually we needed to really look at the trajectory for Juice and for Clipper at the same time, and to look at the temporal and spatial coverage of the system. And as I've already mentioned, we have this interesting approach phase, which occurs after Clipper. It goes into orbit around Jupiter. But then once Juice enters orbit in the middle of 2031, we then have 3 whole years where the 2 spacecraft will be operating together in the Jupiter system. And this chart is useful. Let me just explain a little bit what it's showing. So across the top row is the Clipper moon flybys. So you can see Ganymede in orange, Europa in green, and Callisto in blue. And then underneath are the same flybys for Juice. And so immediately, by looking at the 2 sets of trajectory information together, it allows us to notice some interesting facts about the sequence of events which will take place. So, for example, the blue Callisto flybys are happening at a similar interval in time, covering an extended region around 2033. But interestingly, none of the Ganymede flybys overlap with each other and are actually separated in time. The final thing to note, which I'll come back to in just a moment, is that we have just 2 Juice Europa flybys, and one of them occurs very close in time to E23 of the Europa Clipper flybys. So it's important to mention here that by default, Juice will be making observations throughout the whole orbital phase, but the baseline for Europa Clipper is that it will be operating to study Europa only, so operating through the Europa flybys. I wanted to just show a quick chart on the payload comparison. I'm not going to go into the detail or define all those acronyms for you. All of that information can be found on the respective mission websites. But I just wanted to show the comparison really, as it's perhaps what we would naturally expect, that 2 missions that have very complementary science objectives to assess the habitability of Europa and of Ganymede, and in the case of Juice, to study the Jupiter system. We actually have 2 payloads which are highly complementary to each other. So covering, for example, spectrometry at different wavelengths, we have ice-penetrating radar on both spacecraft, and we have in situ magnetometer and plasma instruments as well. And of course, within the detail of those instruments, there is some difference in the capabilities and different wavelength ranges or resolutions, for example. But there are also some notable differences between the payload, and I think that's where it's interesting, where one spacecraft can add significant value to the other's observations. So, for example, Juice has a radio and plasma waves instrument, whereas Europa Clipper does not. Europa Clipper has the e-Themis thermal emission imaging capability, whereas Juice does not. And just another example there is the laser altimeter, which Europa Clipper does not have. So this is where the missions can add significant value to each other. Okay, so here is the summary table, which shows how our 100 science objectives that we've looked at are distributed across the different bodies and themes that I've mentioned there on the left-hand side, and how you can see roughly how the number splits across those. There's about 100 that we've identified, and giving an initial assessment of the priority of the science, we would assess that 50 of them, about half of them, are considered to be of high scientific value. We've also then just marked according to our description of whether those are synergistic, either simultaneous or coordinated, or the complementary measurements, and how those distribute across there. So don't worry, I'm not going to go into a huge amount of detail on that. I just want to highlight a few of the examples over the next few minutes. Okay, so the first example then are the possibility of joint studies of Europa's plumes, assuming they are observed. And obviously, one spacecraft can individually make the observation of Europa's plumes. However, it's important to note that dual spacecraft measurements would really be extremely beneficial for further identification and characterization of those plumes if they were to be detected. And what we've looked at from the trajectory is that there are 10 opportunities where Europa Clipper and Juice are simultaneously less than 1 million kilometres from Europa and less than 1 million kilometres from each other. So this is just an example of highlighting moments within the trajectory where joint work would be really beneficial. And if we could make those simultaneous observations with two spacecraft, we could learn more about plume gas flow and how it interacts with the exosphere. And as well as including opportunities where, for example, Europa Clipper is doing a close flyby and Juice may be able to look at upstream or downstream observations from Europa. As I mentioned already, there is this great opportunity for a near simultaneous observation during this E23 and Juice E2 flyby. And I'll come back to that in a moment. And this one is just to show you the example of one of our objective slides. So I'm not going to read out all of the details here, but to give you an idea of the work that we have done, we have one of these slides for every single one of those 100 objectives, where we try to describe the observations that we'd like to make a note of the different payload that could be involved in those observations, and then looking at the operations requirements and the instrument requirements, and just noting any additional thoughts and any key references for us to look at. So this one is really highlighting the potential for imaging with visible, infrared and UV instrumentation simultaneously, and recognizing that benefit of the two missions working together if that positive identification of the plumes is made, and then following up together to plan joint observation. The next example I'd just like to highlight relates to magnetosphere dynamics. So if magnetospheres is your favourite topic, then you will know that two spacecraft are significantly better than one spacecraft in a magnetosphere. It's notoriously difficult to work out the difference between temporal and spatial variability. So if you can have two spacecraft, you can make significant progress. So this 3-year interval with the two spacecraft operating in Jupiter's magnetosphere really does provide an incredible opportunity to understand magnetosphere dynamics. And that could be all sorts of different things. For example, looking at Jupiter's aurora in Jupiter's atmosphere whilst measuring the magnetosphere, looking at magnetosphere interchange motion, looking at magnetodisk dynamics, looking at reconnection events, and all sorts of other possibilities. Now, in an absolutely ideal world, these investigations would take place continuously. So we would want both spacecraft to operate the fields and particles data instruments continuously. Of course, Juice will be doing that, but Europa Clipper would not by default. And we recognise that may not be possible. So we also spent some time looking at useful configurations throughout the trajectory where we could focus on intervals of interest. One of which then is to look at the distance between the two spacecraft. So when the two spacecraft are in quite close proximity. So that's what this chart is showing on the left-hand side. This is the separation distance between the two spacecraft. And here I've just highlighted where if we put, for example, a limit on that at 2 Jupiter radius, you can see there are 2 significant intervals of time within the 3 years where that criteria is met. And in fact, this interval here also includes this Juice E2 and Europa Clipper E23 flyby. And that's the animation that you can see of that interval playing out on the right-hand side. So if you keep your eye on that in a moment, you'll see that close Europa flyby with the two spacecraft together. If we relax that criteria to 10 Jupiter radius, we then find that that interval becomes nearly 30 days long. And we think that that is a fantastic opportunity for a magnetosphere campaign. I think maybe we just saw the slide of that. I'm going to keep going in the interest of time. I wanted to just introduce a quick IO example. As you may know, there are no close flybys of IO from either spacecraft, but we do have some IO objectives. This one is highlighting the significant opportunity that exists for remote sensing of the Io torus during the approach phase and also during the orbital phase. And this example here highlights relating long-term measurements of Io volcanic activity to changes in the neutral and plasma torus and ultimately looking at how the magnetosphere responds. So whether that's in situ in the magnetosphere and even looking at auroral activity. I just want to touch briefly on Jupiter's atmosphere. I'd like to thank Lee Fletcher, who came in to assist the steering committee by bringing his significant expertise on how these two spacecraft could bring extra value to Jovian atmosphere objectives. And of course, similar to the magnetosphere, really, it provides this unique opportunity to study the atmosphere from two vantage points, and that's really the advantage that we get that's highlighted on this slide. And that is possible across three areas, one of which is radio science occultation. So basically by adding in examples from Europa Clipper would increase the range of latitudes, longitudes and local times that occultation measurements could be made. We also have a significant opportunity then for dual space views, or like stereo imaging of individual atmospheric features, providing narrow angle and also contextual wider angle imaging information from two vantage points, or even looking at individual features under different illumination conditions. And there's a nice example in our set of objectives looking at atmospheric storms under dayside conditions at visible imaging, and then looking for lightning under night-side illumination conditions. So generally speaking, the atmosphere measurement from two spacecraft adds flexibility, it expands the instrumentation capabilities, and expands the wavelength coverage. I'm not going to go into details of this one again, but just to give you an example, this is number 14 of 14 Jupiter atmosphere objectives. And this one is interesting, which is why I picked it out, looking at the thermal emission of Jupiter's auroras and moon footprints. So auroras generating stratospheric heating that then could be studied by combining the submillimeter wave instrument on Juice with ETHEMIS on Europa Clipper. So that's deemed to be high priority and relatively easy to implement. Okay, so coming to the end of my section then, I just wanted to touch briefly on surface coverage. Now, it goes without saying, I hope, that the Europa ground track comparison here you can see between Europa Clipper in blue and Juice in yellow clearly demonstrates that Europa Clipper is going to cover all of the Europa surface, and Juice will be useful to add extra value where the instrumentation differs slightly from that on the Europa Clipper, as I mentioned, for example, the laser altimeter. And the same goes for Ganymede on the right-hand side. Juice is providing the full coverage of Ganymede, and Europa Clipper is providing some additional coverage closer to the equator. But it's interesting then when we look at Callisto, we can see that the Europa Clipper flybys of Callisto shown in blue are quite different in nature to the Juice flybys, which are shown in yellow. And this is because the Juice flybys take place during that inclined phase, which Claire mentioned at the beginning. And so actually, by combining observations from Europa Clipper with the observations from Juice, could really add some significant new science. And just to bring out one example is the idea of coordinating or serendipitous additional observations of Callisto may be able to provide enough information with previous data sets to allow a determination of the properties of Callisto's ocean. So that's a really important objective which we'd like to advocate for. And finally, just want to show the cross-calibration opportunities, and there are a number of opportunities. For example, here you can see in the E1 Juice flyby, which overlaps with different flybys from Europa Clipper, and that brings about opportunities for cross-calibration of instrumentation as well. Okay, so thank you very much. I'm going to stop sharing my screen and hand over to Mathieu.
So, as Emma mentioned, I'm going to be talking about the cruise and approach portion of the activities of the Juice Clipper Steering Committee. So, as an introduction and a disclaimer, there was a subgroup of the JCSC, the Juice Clipper Steering Committee, that focused on that portion of the two missions, and that group only considered what can be done with Juice and Clipper together. It's not putting any recommendations for individual missions or what they would do during planetary flybys, nor considerations for possible synergies with other missions in operations, which there actually would be many. I'm just going to talk briefly about the Europa Clipper and Juice timelines. So, as you know, Juice launched just over 2 years ago and Europa Clipper last October. The reason I want to touch on that briefly is that there are really three phases that the JCSC has considered for the two missions. We have between their launch and the arrival of one of the two spacecraft at Jupiter, both will be within the heliosphere in the interplanetary space. That's the cruise phase. Then Europa Clipper will arrive first at Jupiter in April 2030. And as you can see, there will be a period of about 15 months during which Europa Clipper will be already orbiting Jupiter, but Juice is going to still be in between the Sun and Jupiter within the heliosphere. So we'll have one spacecraft in the Jupiter magnetosphere while the other is outside of it. A very unique configuration. That's what we'll refer to as the approach phase. And then, of course, once Juice arrives at Jupiter, then we'll be in the orbital phase that Emma just talked about. So this interplanetary cruise period is really interesting because we have two spacecraft that will span a fairly large range of heliocentric distances between 1 and 5 AU at very different times. And what this will allow to study is how solar wind shocks, co-rotating interaction regions, solar wind transients such as coronal mass ejections, and general turbulence within the heliosphere then evolve and propagate. So that's a very unique thing that we can do having those two spacecraft. In addition, obviously, being in the interplanetary space, there will be opportunities to measure interplanetary dust particles, galactic cosmic rays, and interplanetary hydrogen. And last but not least, as you can see at the bottom left here, we are actually nearing the peak of the solar cycle 25. And so this will give a unique opportunity to follow the activity of the Sun throughout the peak of the cycle and then its decline afterwards. So during the cruise phase, we have established several science objectives. For shock and particle acceleration, solar wind transients, and solar wind in turbulence and heating, all of these are really measurements about particles from the solar wind and how they are distributed within the heliosphere, propagate, and evolve as a function of time. And then, obviously, as I just mentioned, we want to follow closely the activity during the solar wind cycle, the solar cycle 25. So most of this will be done with the in situ instruments on both missions, plasma instruments as well as magnetometers, etc. We want to survey the interplanetary dust particles. That is something that can be done extremely well with instruments like on the Europa Clipper, the surface dust analyzer. Once it opens its cover after 2.3 AU, you'll be able to make measurements. I mentioned galactic cosmic rays. Again, that's going to be primarily plasma and fields instruments. Interplanetary hydrogen can be followed fairly uniquely using the two UVSs on both spacecraft by looking at each other and looking away from each other in order to then derive the column abundance of hydrogen in the space between the two spacecraft when the measurements are made, and that can contribute to better understanding the influx of hydrogen from interstellar space. We also want to understand Jovian electrons and their contribution to the heliosphere. There is also a great opportunity to study Jupiter full disk from afar as we get close to it, and that would be an interesting simulation of what can be seen by, for example, the Habitable Worlds Observatory at exoplanets that are like Jupiter, so that can inform those science objectives and measurements that can be done there. And lastly, we also want to study solar radio bursts, which can predictably happen and then be measured, for example, in the radio as with Rhyme and Reason and Juice and Clipper. During the approach phase, as mentioned earlier, we'll have Europa Clipper for 15 months inside the magnetosphere and Juice outside of it. So that's going to be a really unique opportunity to have a direct measurements of what the solar wind influx to the magnetosphere is, while we'll be able to see with Europa Clipper how the magnetosphere responds to that. And that will help understanding internal versus external sources of influences of the magnetosphere. So, for example, how do major disturbances in the solar wind impact magnetosphere behavior near the moons, within the disk, in the tail, as well as auroral dynamics? And how does that compare with the activity that is also brought in via IO? So there is a lot that can be done there. And in addition, we want to study outer irregular satellites. And again, as was done previously, as for cruise, Jovian electrons, exoplanet analog options, study options, solar radio bursts. And lastly, there will be a great opportunity to measure the Io torus in 3D from within and outside the magnetosphere. That will be an interesting complement to the Io torus objectives that Emma just talked about for the orbital phase. So obviously, if things were ideal, we would want to operate all of the instruments all of the time on both spacecraft. However, this is unfortunately not feasible. There are of course limitations on power availability, downlink, as well as agency resources to operate the spacecraft. So as a starting point, what we did is consider 3 optimum spacecraft configurations to enable the accomplishment of the science objectives. Those are inspired by the work of Khalid et al. 2021. I'll just go very, very quickly because I see that we're running out of time. I want to leave time for questions. So the first one will be to have the 2 spacecraft in the same heliospheric longitude range from the sun. That's what you can see in this little sketch here. That is a configuration that will happen in late 2029 and early 2030 for about 6 months, and then during the approach phase. Another interesting option will be when the 2 spacecraft are at the exact same radial distance from the sun, and this will happen in mid-2026 for about 2 months, and then again in the approach phase. So fairly sparse opportunities there, but those will be very interesting nevertheless. And the third one would be the Parker spiral connection. So that's when you have the magnetic field line from the sun that go all the way to Jupiter, and the 2 spacecraft aligned within them. And these will happen at different times. So bear in mind that those times are a function of assumption on the speed at which the particles will be traveling from the sun. There will be an opportunity in early 2026, and then through most of 2027, and again in the approach phase. So there are several of these opportunities that are fairly unique configurations that can be really useful to accomplish the objectives. The cruise phase is going to be very interesting because we'll cover a broad range of heliocentric distances with 2 spacecraft. The approach phase is truly unique because we'll have 1 spacecraft in the magnetosphere, 1 outside. And of course, this could be coordinated with other spacecraft within the heliosphere, Parker Probe, Solar Orbital, Bepi Colombo at Mercury, Maven at Mars, Psyche, as well as ground-based and space-based telescopes. So there are many, many opportunities to expand on what the JCSC considered for those opportunities. And the last thing I want to point out is that we just rotated the Juice Clipper Steering Committee. You can see here the new members that are incoming, and the primary goal will be to review the report as well as feedback that has been received by the Juice and Europa Clipper teams to then evaluate that feedback, adjust objectives as needed, and then focus on how to really implement those with the missions and the payloads. And I'll stop here. Thank you very much.
Thank you so much, Mathieu. Thank you so much, everybody, for your beautiful presentations. Exciting times coming up. Questions from the audience for our speakers. So here, Jan Bergman is saying that most of the Juice instruments, they are off during the cruise. They are not online. To what extent would it be possible to switch them on a little bit still? I don't know, maybe that's a question for Claire or Olivier.
Yeah. Well, it's not completely correct in the sense that I mentioned at the beginning of my status. We will operate the instrument at a regular pace, more or less every 6 months, for a period of 1 week. And we also now have extended this scheme to also operate for a few months later on when we will be a bit further away from the sun. So in that sense, we have regular operations from the instrument. But of course, we will look at maybe further possibility to extend this, but this need, of course, more deeper analysis, let's say, on the feasibility. Yeah.
Hi, Claire. And everybody.
Hi.
Yeah. Well, as I mentioned, we have this idea to use SRAM memories as monitors for cosmic rays and high energy particle events. And for that, of course, we would have to be on as a radar is on all the time. But I don't know if that is feasible or not. That would, I mean, it will not burden Juice with science data because those events are reported by housekeeping. Can you comment on that?
Well, Radem will be on continuously, as you know. So this is not of concern for
yes,
for
in safe mode.
What do you mean by safe mode?
On only the power supply and the DPU, basically.
Okay. Well, I think this is something that we need to discuss also within the science team on Juice to see if there is a strong science case. Then we can probably investigate the possibility.
I don't know how strong the science case is, but we have started to discuss with the Radam team and also other payloads. It has been used before on, for instance, missions like Mars Express, Rosetta, ongoing on Bepi Colombo, and also with Swarm with 10 years of data.
Question by Grace Richards. I saw that Bepi Colombo was mentioned for possible scientific synergies. What kind of science would be possible between the Jupiter system and Mercury? Tracking solar events, solar wind properties? Question mark. Who wants to comment on that?
Carry on, Martin.
Yeah, I was going to say, yes, that's exactly right. That's exactly the type of things that we can do, including with the other spacecraft in the solar system at that time. Emma, I don't know if you want to add anything. Go ahead.
No, that's absolutely right. And I suppose the other thing that we can also think about is things like Parker Solar Probe and Solar Orbiter, so we can track activity on the sun, how it influences the inner heliosphere, and then we'll have potentially the opportunity to see how that evolves out to the orbital heliocentric distances between Mars and Jupiter. So as Mathieu has described, we have a fairly rare opportunity to have 2 vantage points potentially, given the conversation we've just had about the instruments being on. But assuming we could have some intervals where they can operate together, that will be a really interesting sort of large-scale space weather observation, which is really an important topic for our own planet. And so, if we can study space weather in the heliosphere by having these multiple measurements, that would be really of great value, I think, across a lot of disciplines.
Yes, we had, during the Payload Checkout 3 with Juice, we had an event lasting for 15 minutes, where it was on the 31st of March, by the way, where we believe that we have seen a CME. And we are now looking into data from Parker and Solar Orbiter, which was not straight on line, but the angle was not that great. I think Parker was something like 6.5 degrees from use or something like that. So there are opportunities, and this was such an opportunity. We got a hit by capturing data for 15 minutes, basically.
There's a question by Katie Knowles regarding future collaborations between Juice and Europa Clipper with space-based telescopes, such as the James Webb Telescope. How do we coordinate potential collaborative simultaneous observations? I guess that's a good one. Go ahead, Bob.
Bonnie Barati, JPL Deputy Project Scientist for Europa Clipper, has been organizing a group of observers to monitor the system and help support the missions. So I recommend, if observers are interested and not already part of this group, please send an email to Bonnie Barati at her JPL address. Maybe someone could put it in the chat for us to get up to date on the activities of that group.
Okay, thank you.
Thanks, Bob. Can I just comment as well, if we've got just a minute?
Yeah, go ahead. Yeah. That's
really great that activity has already started. And oh yes, you can see Bonnie's email is in the chat now. And we've seen how successful this can be, looking at the Juno mission as an example. That there was a great coordination effort which was led by Glenn Horton from JPL, and they really got their act together and had lots of people proposing for telescope time in a very coordinated fashion. So we've got a really good model for how this can work. And of course, what the missions and project leads can do is to help provide support to those observers to try to emphasize the importance of winning some of that very precious, very oversubscribed telescope time during our missions, and that will be an extremely great way of helping scientists to get that telescope time. So hopefully that's something that we could potentially help with our joint committee as we go forward.
Definitely. And just to comment on that, we were just at the science working team from Juice last week, 2 weeks ago. And of course, there was discussion about the amateur pro collaboration. There's a lot of amateur coordination as well, which has proven very useful for Juno, which will prove very useful for both Juice and Europa Clipper as well.
I just wanted to comment as a follow-up to previous questions that we, Europa Clipper, do not have the go-ahead to do cruise observations, or for that matter, observations in the tour that are science related and related to this coordination. But that conversation is occurring with headquarters and within the project. So discussions like this can help that effort.
Let's close this webinar. Thank you so much to all of our speakers. Thank you so much to all those participating. It's been a great webinar. Looking forward to this beautiful 2 missions successfully arriving at Jupiter and doing great things together. So we will close the session for today. Thank you so much, and see you at the next Juice webinar.
Bye, everyone.
Bye. Thank you.
Thank you very much.